Hello everyone. So here we are, we're going to keep working with our quadratics or our parabolas, except now we're actually going to apply it to real life. We may have done some of this previously, but we're going to do a little bit more with it now. So we remember going back and identifying, we looked at last time with our calculators, identifying some critical parts. So we identified the y-intercept, the x-intercepts. We looked at the vertex. Now we're going to break that down into both the x part as well as the y part. Then we also looked at finding some random coordinate point. So we previously looked at finding it when coordinate point when x is equal to -10. That's what it was in your last homework. But now it's going to be looking at it with just different points. It won't always just be -10. So we need to match each of these coordinate points up with a real life application. So remember, we're going to be looking at, do a little sketch up here. We're going to be looking at our parabolas. So we're still going to have shapes looking like that. The majority of them are going to be concave down, but you may see them where they're concave up. So we're wanting to identify each of these things. So first off, our y-intercept, or right there, wherever we cross the y-axis, that we can match up and put in real life terms of what height did the thing start at. So if we thought this was a rocket, maybe we're shooting the rocket off from the top of a building or something. I don't know, just you may not always be starting on the ground. Okay, the x-intercepts right here, those are going to be, if we're starting off at a height, the x-intercepts are going to be the equivalent of wherever the thing hits the ground. So it could be a rocket, it could be whatever it may be. Okay, then we're also going to have to look at the vertex. So with this one, it'll be our highest point. So the y part is going to tell us, so our coordinate for our vertex is going to be x and then y. So the y tells us what's the maximum height of the thing. And then the x is going to tell us the time it takes for the thing to hit its maximum height, or the time the thing is at its maximum height. The thing, again, arrow, rocket, stone, whatever it may be. Okay? And so that leaves us with the coordinate point. It's just what's the height at blank seconds? So if we're saying, hey, 2 seconds into this rocket's flight, where's it at? So we could have it right here, just wanting to know what height it is at that time. Okay, so using that information, we're going to go and apply that to some real life scenarios. So looking at this one, a rocket carrying fireworks is launched from a hill above the lake. The rocket will fall into the lake after exploding at its maximum height. So the rocket's height above the surface is modeled by the parabola below. Okay, so now let's kind of decode this. What height does the rocket start at? What height does it start at? So that'd be this one, which would be the y-intercept. So for this one, we need to find the y-intercept. I'll just do y-int for short. How high is the rocket after 1.5 seconds? So what is the height at blank seconds? So that's going to be a random point, or the point, so I'll just say random point. Okay. What height will the rocket explode? Well, it says that, again, the rocket will fall after exploding at its maximum height. So it's going to explode at the maximum height. So the maximum height of the thing, that's going to be this. So that one matches up with the y part of our vertex. So y coordinate of vertex. And then how long will it take for the rocket to hit the lake? So we're launching it above the lake. So the x-intercepts tell us where it hits the ground. So this is what we're going to want to know is our x-intercept. Okay? So now let's identify those points. So here we're given a graph. So if we're given the graph, we can just look at the points. So the y-intercept is right here. So at what height does the rocket start at? It's not giving us a unit for this one, but we could just say, I don't know, just assume it's like feet. So 80 feet, because our y-intercept is at 0, and then 80. Okay, now how high is the rocket after 1.5 seconds? So our x-axis is seconds, so we gotta find where 1.5 is, which is right here. So then if we just follow that line up, we get right there. So our point at 1.5 is 140, so it's going to be 140 feet. How high will the rocket be when it explodes? So we're looking for our vertex, which is right there. So it's going to be at 2, and then, I don't know, 140, each line's 10, so that's like 2 and then like 145-ish. So this would be what height? The y-coordinate of our vertex is, like I said, 145 about, so it'd be 145 feet. How long does it take? Will it take the rocket to hit the lake? So we only are given one of the x-intercepts, which is right there, which is at 30. So it's going to take about 3 seconds. Okay, so that's how we do it there. I'll leave you guys this one. Number 2, a rock is thrown from the top of a tall building. The distance in feet between the rock and the ground t seconds after it's thrown is modeled by the parabola. And so at what height was the rocket thrown? So that again will be our y-intercept. How long after the rocket is thrown? Is it 370 feet off the ground? So we want to know the time at 370, so that's going to be a random point. But more specifically, that's going to be the x-coordinate. How high is the rock after 3 seconds? That again is going to be a random point. Okay, I'll trust that you can find those. If a person is walking under the building 4 seconds after the rock is thrown, will the rock hit the person? So we'll do that one. So at 4 seconds, if we come right here, if we go up, this is again technically a random point. So here we're about at 4 seconds, the rock is still like 100 and I don't know, maybe 105 feet above the ground. So if we think about that, if a person is underneath there at 4 seconds, are they going to get hit? Is the person 105 feet tall? I don't know of anybody who's 105 feet tall, so the answer for this one would be no. How long does it take for the rocket to hit the ground? That is an x-intercept. Okay, so that's how we do it based off of the graph. Now, as you can see in number 3 here, 3 and 4, the path of an arrow shot in the air can be modeled by the function -3 parentheses x minus 4 end parentheses squared plus 142 where y is the height in feet of the arrow above the ground after x seconds after it's released. Okay, so now we got to go based off of an equation. So what we got to do, last time we learned how to use our lovely graphing calculators. So we just go ahead, whichever version you have, you type it in, -3 parentheses x minus 4 squared plus 142. Graph it. Man, we can't really see much of it. So we have to adjust our window. You can't really see our y-intercept, so we got some big numbers with 100. So let's change our x max to like 100. Let's change our y max to like 200. And let's see if that shows it to us. Okay, so we got a graph there. Maybe not quite that much that we need. Let's change our x max. Let's do like x max to 20. Okay, cool. So we can see our graph. So once you get our graph, now we need to find the different parts and identify what we need to find from the graph. So what is the maximum height the arrow reaches? That's the y coordinate of our vertex. How many seconds does it take to reach that height? That's the x coordinate of our vertex. And then we got how high will the arrow be at 6 seconds and 8 seconds. Those are just random points. And at about what time will the arrow land on the ground? That's an x-intercept. Okay, so now we're going to use our calculator to go ahead and find those. So we go ahead, whichever calculator you have. If we're looking at our graph, it's concave down, so we're going to use the maximum function. So we go maximum. If you're using a TI, you got to go to the left of it, to the right of it, guess where it's at. Okay, so the y coordinate of our vertex turned out to be 142. And so the maximum height the arrow reaches, it would be 142. And then our units are feet, so it would be 142 feet. How many seconds does it reach that height? So our x is 4, so it's going to be 4, and then our unit again was seconds. Okay, so how high will the arrow be at 6 seconds? Those are random points, so we use our good old value, or on the TI calculators or on your Casio calculators, it will be using the y-cal. So then we type in x equals 6, we get a point of 6, and then 130, so it'd be 130 feet. Then we gotta do it again to find the 8 seconds, so value x equals 8, so we get a point of 8, and then 94, so it'd be at 94 feet. Okay. If you're having problems with the calculator, go check those little cheat sheets, check the other video, those are there to help you. Or, as always, reach out and let me know if you have any questions. At what time will the arrow land on the ground? That's the x-intercept. So if we look at our graph, there's like one that's to the left of the y-axis and one to the right of the y-axis. We need to find the one to the right. So we use 0, or if you're in your Casio calculator, you use the x-cal, and you just put in a value of y equals 0. On the TI calculators, you got to go to the left of where you think it is, to the right of where you think it is, guess where it's at, and that gives us a point of 10.88 and then 0. So that would be about 10.88 seconds. Okay, so that's how we do it based off of a equation. So for this number 4 here, we would do it the exact same way. Just to help you out, what we would need to do, what's the ball's maximum height? That's the y coordinate of our vertex. How long does it take for the ball to reach that maximum height? That's the x coordinate. How high will the ball be after 5 seconds and 2 seconds? Those are random points. Then at what time will the ball bounce on the ground? That again is our x-intercept. So go ahead, see if you can figure those guys out. Make sure to clear out your calculator, change your window back to normal, and then go ahead and find those. As always, reach out if you have any questions.